Okay, video number 7 in the How to Wire Schneider Modicon TM3 expansion modules video. Today we're going to be looking at a very specific type of card. It's one that's got an NPN transistor style of output, which allows us to create syncing DC outputs. Before we begin, though, we are going to start with a word of caution, as we always do anytime that we're looking at syncing outputs, because syncing outputs can create danger from unwanted load operation. In other words, the load's going to turn on during a fault if the DC supply is grounded on the negative. If you have an ungrounded DC supply, it's not going to be an issue. If, however, it is a grounded DC supply, there can be an issue. And do take note that this only happens if there is an actual fault. Not, just day by day that it can randomly pop up. You still need somebody to actually ground fault some type of an issue. Anyways, if you're unfamiliar with what the danger is with these, go to video number 2 in the M221 series. You can watch through that. We have a fairly detailed explanation. All right, let's look at the units that we're going to be using inside of here. The modules that we are looking at all end in a letter U. And specifically, the one in this video is going to be a TM3DQ. That's going to be a discrete output, cubing output 8. Telling us the number of points that we're going to go and have, and U telling us that it is a NPN, or a syncing style of output. What you learn inside of this video, you can also apply to these. If you've got these ones, they're just expanded. They have a few more I/O points that are going to be off of them. You're going to have to distribute, positive, negative to a few more points off of them, but it's the exact same format we would be looking at. All right. So what is syncing? Short form, syncing is going to be applying a direct connection of the negative to a reference or to a common terminal, and in this case, it would be considered to be an application of IEC negative logic. Let's start with our data sheet. Inside of here, we see that this specific set of modules that we're looking at are usable across basically the whole Modicon family, 221, 241, 251, and 262. We do see that they are going to be a DC transistor output, which tells us that we can't run AC through them. Anytime you get a transistor, it's strictly going to be DC. They tell us that it's going to be 24 volts DC transistor output. It is a syncing type. And then down over here, we have the amount of current that we can drive through it, 50 milliamps. So very, very small amounts of current that you're going to be able to drive out of these cards. Remember that the relay cards had 2000 milliamps or 2 amps that was going to be available. These are going to be much, much smaller. So be careful the size of the load that you try to drive with one of them. They give us a little bit more information as well inside of our data sheets over here. Time to go and turn on. If you take a look at this, it's 450 microseconds to turn on or 450 microseconds to turn off. You compare that with the relay, which is going to be in the 10 and 50 microseconds turn on, turn off. You see that these are a much faster acting. And that's really the benefit of the transistor is, solid state. It's got no moving parts. It can switch extremely fast, and it can switch an almost, innumerable amount of times. Whereas the relay ones, you've got a limited lifespan that's going to be available to them. There is going to be leakage. All semiconductors will always go and leak, so you can expect to go and have 0.1 milliamp or about 100 microamps of current that is going to continuously leak through these. Be careful with very, very low power loads, because sometimes it's not enough to activate a load, but when you try to turn off a load, it can be enough that that load maintains its power. And there's multiple ways to go and deal with that. There'll be more video series where we'll start dealing with some of that stuff on the practical wiring end. Careful with your distances, you're going to run them as well. 30 meters is going to be your maximum that you're going to go and look for. And then outside of that, they don't tell us, much more that we're seeing over top of these ones, that's really critical to us. They do show us this over here. This is not a voltage rating that you're going to bring for an input. It's just telling you about an insulation rating. You're still only bringing in 24 volts. All right. Let's start by taking a look at our wiring. Remember that we are dealing with syncing, and syncing is going to be direct application of my negative to my common. So we're seeing that down here. They're taking the negative from their external power supply. They're sending it in there. This section over here is basically going to be your negative that's going to get distributed out like that to all of your outputs there. It's to get switched through the inside. And then you also do need to go and apply a negative and a positive over here. We can see that the positive feeds through to the card itself just to go and run, and we'll just draw it here in green because that's the color most of them are, the actual circuit board that is going to be inside of here that takes care of all of that switching. So you do need to have both positive and negative to it. In this case, like we said, positive and negative supplies the microelectronics, and then this is the one that is going to get switched by the microelectronics through and out to all of your components. We got a couple symbols on here as well that we're going to go take a quick look at. First symbol that we see over here is going to go and be this. This is going to be the symbol for a fuse. That is going to be in line with our power supply. We do see that that fuse is going to be 4 amps up top over here, and then they're dropping down to much smaller fuses across the actual outputs themselves of just half an amp. So one master fuse that fuses the whole group, and then subdividing down. Inside of our drawing, we're only going to use the master one just because otherwise it gets too crowded with too many fuse holders, but more protection is always better. We're going with the absolute minimum. This over here is going to be the load we're trying to go and switch, and if we follow through, what we should see is that there will always be a complete path for current through my entire circuit that would allow my load to go and switch on. We see the negative switch through there. We see the positive brought over to it. All right, let's take a quick look at what we're going to use for fuse holders, DIN rail mounting, along with everything else that we have inside of there for our PLCs. I suggest using a DIN rail mounted one. It's just way easier to go and run with there. They do suggest inside of their manufacturer's documentation type T fuses. These can be hard to go and get fuses or fuse holders for. You could use CCs with an HCLR type. That's going to be extremely fast acting, or you can use these type over here that are going to go and have the small glass or ceramic fuses. Both of these you will see have got a lit section that's going to tell you when you've got a fuse out inside one of the holders. It's just a easier way to deal with your troubleshooting later on. All right, now we are at the actual wiring part itself. So we'll zoom in over here on my actual unit over here. We see we've got all of the inputs, outputs. This is the unit we're looking at, the 8U. It's a transistor output syncing. They're labeled on there 0 through 7. We see that the PLC that we are running the entire thing off of is going to be the 251 over here. So that's our main brain. And then we're going to follow through our power distribution just up to where we are at. So we see we got AC taken in through a DIN rail breaker. That AC goes into a DC power supply. That DC power supply, we take the positive out of there, we run it through a DIN rail breaker. We see that we are bringing a positive in here that's going to be running my main CPU for the system. And we also see that we take that DC over and we're going to drop it off over here at this fuse. And this fuse is what we're going to go and fuse for our outputs. It's going to be that 4 amp one that we saw in those previous diagrams. Okay, because we are working with a syncing style, the very first thing that we are going to do is we are going to deal with the distribution of our negatives. So we're going to come from our DC power supply over here, and we are going to go and run that up, and we will run that in and in onto the V negatives that we are going to have over there. The next thing that we are going to do is we are going to go and take our positive from here, and we're going to go and apply it to this card as well. And by doing that, we've now brought power over to run the actual card itself. Okay, next step is going to now be running this positive as well from here out to my actual load. So we're going to go and do 2 runs over here. We're going to go and take this one up here to the A1. That's going to be the coil. You'd be wanting to use very low power loads for these because it's only 50 milliamps. And then we're going to take that power over here to the normally closed. This block over here is an overload block. For those of you who aren't unfamiliar with it, it senses the current running through this contactor and it trips it out if your load gets too much current pulled. So then we're going to run out of that normally closed up to my A1 like that. So now we've brought our positive over to each of our loads. We're going no more than 2 wires underneath a single terminal. Last thing that we would have to do now is actually run out our switching that we are going to go and have. Remember, we are switching the negative. So we are going to go and take a negative out of any one of these. We'll start here off of 0, 1, and we will run that thing around, and we will run it in to my A2 coil. And we'll take another one off of another one of these. It really doesn't matter which one. We'll take it off of number 4 over here, and we will run it into that A2 over there. Last thing that you should be able to do would be track through all of your wiring to ensure that you've got a complete path for current. And we'll do that here. We'll take our positive in, we take our positive through. We can see that we can take the positive up, we can run through this coil, back down along my return into here to my negative through the card, and all the way back to the power supply. As long as you can trace a complete path like that, you have got operational setup inside of here. This one over here is a little bit different because of that, but we can trace to that one as well just as quickly. Positive over through my fuse holder travel up, junction underneath that screw, we're continuing our power. We travel through the normally closed contact that's inside of there, up, hit my coil, travel through the coil, energizing the coil, and back through to my card, travel through the card, back to my negative and home. So both of these work. Where is the danger for this? The danger for these is always going to be when we are dealing with a grounded DC supply. This DC power supply is not inherently grounded, but sometimes you will see that people will ground their DC power supplies the way that we have just done over here. Where the danger would be is if one of these two cables was going outside of the panel to a field device or something like that, and if it ended up getting accidentally grounded down, we would have a path back through. And we'll just do that here off of this one. Say that that thing got accidentally grounded. There's a fault out inside of that system, which would mean that now my positive can travel through here. I bring a positive to the coil. From the coil over here, I come back along here. And now I don't need the PLC card. I can just travel back through my bonding system, up and back here, and I'm back at my power supply. So we'll have current flow and I'll have operation. This is the danger that we see with these ones. So be careful with your wiring, how it's run, how it's shielded and things like that. If the DC doesn't need to be grounded, then don't necessarily ground it at all times either. All right, that's it for this card.